Okay, so here's a definition. You've actually got this. I put this on your homework. I think it's like good for us to record it. Uh, Greatest common divisor. Someone called D. This notation, greatest common divisor, as you may guess, is a common divisor. Uh, you know, what do I mean by that? Well, I mean that D divides M, D divides M. So when I divide D into both of these things, I get 0 for the remainder. Here's the rub. What do I mean by greatest? Such that if D prime is any other common divisor, M, then D prime divides D. So it's this extra special common divisor, such that any other common divisor must divide again. And these things actually do exist. You'll see that on homework. There's a similar definition for least common multiple. Well, what's this animal? Well, it's a common multiple. So that means that it's kind of the other way, right? Instead of dividing into M and N, it's divided by M and N. And what do I mean by least was special? If L prime is any other common multiple of N, then L divides L prime. So it's the most economic common multiple. Okay, so here is something that you have on your homework, but again, I'll record it here. Theorem. Uh, Let M in not of 0, 1, STD. These things both exist. So given that definition, it occurs to me, I mean, while the greatest common divisor exists, then you can find a common divisor, but maybe there's other common divisors that don't divide it, but that's not true. It's always, these both exist. 2, this is actually super special. This is a very powerful property. The GCD of M and N can be expressed as a linear combination of M and N. You can find integers A and B. So if I have two numbers, like, yes,
Is that supposed to be good GCDs or GBs?
it's about being recreational, but you're right, that's correct. D is a linear combination of M and N. This is actually a very important part. So for example, if you have two integers where the GCD is one, then you can always express one as a linear combination. That's kind of fantastic. And three, there's an intimate relation that comes to. If you take GCD and multiply by the LCM, you get N and N. Right. There are some other properties that these enjoy that are in your homework. Okay, any questions? Okay, I'm gonna do some more practice with proof here. And then we're gonna move on to some set theory, which everything we do will be sort of practicing proofs. Only now we're going to learn some mathematics and prove the mathematics as we go along, at least most of it. This is a classic. Tell me, how many of you have seen this? How many of you know this, right? It's like a folklore thing, right? Everybody's quite heard of it. Right? How many of you have seen this proof? Okay, that's maybe a couple. Well, so how do we do this? I'm gonna make this claim that square root of 2 is not a rational number. This is a good example of maybe proof by contradiction. Right? Let's suppose, well, it's either a rational or an ain't one, right? So let's suppose let's take let's deny this. Suppose radical 2 is. And let's reduce to do something ridiculous from it. What does this mean? What would have to happen if radical 2 is right?
You can express that as an integer over.
Sure. Now let's make my life easy. Give me some conditions that must hold. Well, what's one thing that's true of B?
Not 0.
B is not zero. But there's another condition that we can assume, and it's convenient. We've been talking about the properties of integers that will make my life a little bit easier.
Is it B squared?
Well, we're going to get to that, but for example, what can you always do with your fraction? Right. So this will actually fall from your homework. We'll do this carefully. Let's write this. Let's factor this fraction, right? Integer on top, integer on bottom. What am I going to do? I'm going to jerk out the greatest common divisor, right? I've already claimed this exists. And what is true of A prime over what's the greatest common divisor for this? In other words, A prime and B prime have no factors in common. Okay. You actually prove this on your second, whatever the homework you're working on now, third, I guess. Okay, so now I'm going to get to Daniel's step here. Square this. And what move forward did I make? Well, square root of 2 is very confusing to my pea size little brain, so I turned this into a. Everything's now integers here, and I can make this even better by doing this. I like this equation because it involves nothing but integers, no more confusing fractions, right? Anybody see what ridiculousness we can come up with here? Yes.
Basically, it's saying that a squared is a factor of b times, like b squared times 2. That can be the case, the greatest common factor.
Well, I think you're on the right track here. So 2 divides a prime squared, right? Yes.
Based on that, I think the here is the b squared must then divide a squared.
Okay, we're getting there. We're getting there. But let me ask you this. What kind of special number is 2? It's
To be defined, if we root both sides there, that square root 2, which we defined as a rational, divides a prime, and you said that the greatest common divisor cannot be greater than 1.
right, but you're talking about rational numbers now, so you gotta be a little careful, right, when you talk about division. What kind of special properties do that? What distinguishes it among the integers? That's right, it's synonymous, it's irreducible. So what does that tell me? If 2 divides a prime squared and 2 is prime, then this is a product of 2 things. It's a prime plus a prime, right? And since 2 divides the product, it has to divide the single one, right? Everybody okay with that? And this is actually a step forward. And you do need prime, right? Because notice, we do a quick example over here. Notice that 9 divides 6 times 6, right? It's 9 certainly divides 36, but it doesn't divide 6, does it? Right? And so prime is very important. Okay, so what does this mean? 2 divides A. Well, this means that A prime is to a double prime. I don't go crazy with rounds here, but everybody agree with it? So let's go back to this equation. So now I can rewrite this as 2 . Replacing that A prime with 2A double prime, right? Looks like I'm going in circles. Cancel 2 here. Now, this is going to go on and on forever, right? What can I conclude now? 2 divides B prime squared. So what can we conclude? Again, 2 is prime. So 2 divides Everybody agree with that? And that is the problem. Somebody tell me why?
Assume that there's possible divisors.
We now have two divides A prime and two divides B prime. But ridiculous, but we already assumed the greatest common divisor of A prime B prime is one, but I got a factor two of both of them. So what we assumed has to be ridiculous. So square root of two cannot. Questions on that?
A double prime.
Well, at this point here, I have two divides A prime, right? What does that mean? That means that A prime is two times some other. That's all that is. Other questions? Here's. Example, two more of these maybe. Uh, uh, no matter what integer I plug into this polynomial, I always get an odd. Any ideas on how to prove this?
Put in an even number. Then. An even number times any integer is still even, you're adding one to that, so it becomes odd. We put in an odd number. The square of an odd number is odd. And 3 times an odd number is odd, as well as 5 times the square of an odd number. So when you add those together, you get an even number. When you add one to an even number, you get an odd number.
He's correct. Everybody get that? Maybe not, let's write it down, but you're absolutely correct. So let's take this apart here. And, you know, it probably, here's a good thing to do at the beginning. What does it mean, to be even and odd? Everybody agree with it? What it means, be even is multiple two. Well, and here's another way to think about this. What it means to be odd is when you divide it by two, you get a remainder of one, right? Okay, so I'm gonna do just sort of what Daniel said, I think, I'm doing cases, right? Case one, n equals 2m is even. Here m is an integer. So if you look at 5n squared plus 3n plus 1, this is 5 times 2m squared plus 3 times 2m plus 1. And this is going to be 20m squared plus 6m plus 1, which is 2. Two times an integer plus 1, so this is off. Everybody agree? Case two. Okay, this is a little bit more icky, but it's all right. Well, let's see, that's going to be 20 m squared. Plus 20 m. Plus 5. Plus 6 m plus 3. Plus 1. And so this is going to be 20 m squared plus 20 m. Well, it's still 26 m. Squared is 6 m plus 8 plus 9. That step, but I broke it down a little bit. So it's 2 10 m squared plus 13 m plus 4 plus 1. 2 times an integer plus 1, which is all right. Yes, that's covered by E.
I mean, 0 is equal.
0 is equal, it's divisible by 2.
I also mean 0 is odd.
No. Yeah, because think of it this way. Take whatever energy you want, divide it by 2. If you get a 0 remainder, it's even. If you get 1 as a remainder, it's odd. Okay, here's another one. I'm gonna throw this in kind of as a little theorem, because this is good to know. And you all probably know this anyway. Theorem. Suppose I walk up to you on the street and give you 2 rational numbers. If you multiply them together, you add them up, you will get a rational number. Everybody knows this, right? Or you're familiar with it, you add 2 rationals, you get a rational. Let's prove this. Okay, what does it mean to be rational? I think you've heard that already today. A over B, where A and B are integers and the denominator is not 0, right? So what does it mean for alpha and beta to be rational? A over B, right? So let's let alpha equal A over B and beta equals C over D. A, B, C, D in integers and B, D, D, D. Not zero. Don't want 0 denominator. Okay, if I'm going to be super careful, it's always good to be super careful. Write down what everything is. Alpha is what? How do I add to fractions? Yeah. You probably learned this when you were in grade school. You know, you can get the least common multiplier. Let's not just do that because I am a lazy man. I can certainly do this. And then what? A, D plus B, C. I don't claim that's reduced, but I don't care. I didn't ask for this to be reduced. Here are the big points here. Plus C. Where do these things live? This is kind of a basic point that I'll let you assume all of it. They're integers, right? And if I'm gonna be really careful, what do I need to say about this? Good. This is not zero because B is not zero, D is not zero, so their product is not zero. So alpha plus beta is a rational number because there it is, quotient of two integers and the bottom one's not zero. Right. And the product of these two is that's easier. And again, both integers. AC, BD are integers and BD is not. So the product is in fact a rational number. Okay, any questions on that? So as we go on the belts mathematics, and we're gonna be proving more and more stuff along the way. This chapter is again sort of the foundations, sets, vectoring. Now, so what I'm gonna have to do here is find what set is. I'm gonna, in the next homework, I'm gonna tell you some of the habits you think about sets. We will be working mathematics in this course. I'm not gonna get too far into the logical needs, but there can be, if you're not careful, some hazards about thinking about the sets. I want to first develop an intuitive notion. How many of you have heard of the notion of set? You've probably even used it in conversations with your friends about courses, right? What a set is intuitively is it's a collection of things, sometimes in a specified universe, right? And my rule about sets is going to be, if I have an object in the universe and you give me so you've got a set contained in some universe, and there's an object in that universe. If I ask you about that object, you can tell me whether or not that object is in the set or not, right? So for example, the set of people in this room is the collection of all you all and me, right? We might look at the set of all people that have blue eyes in this room, right? We might look at the set of people who drove a vehicle to come to school today, right? These are all sets, and I can figure out in this universe being this class, whether somebody is in these sets or not by checking if their eyes are blue or asking if they from school, right? So that's basically the notion of a set. It's a collection of something. Sometimes we call these objects or elements in the set. And there's a way to determine in the universe if some object is in that set or not in that set. Now, let me kind of give you a little teaser here about what some of the problems would be. Can anybody give an example, given just what I've said so far, of a set that contains itself as an element? What's that? The set of all sets, right? And it turns out that that's where the logical problem comes. In fact, this notion, there was a lot of controversy, mathematically speaking, not a very long time ago, like 100 years, so a little more than that. There was a lot of controversy on this. Well, let me give you another one. How about, it's hard to imagine a set containing itself as an object, isn't it, right? For example, if I say the set of all people in this room, right? Is the set of all people in this room a person in this room? No, it's something completely different, right? The set of all cars in the parking lot, right? That's not another car in the parking lot. But if I said something to you like, consider the set of all abstract thoughts. That itself is an abstract thought, right? So it can be a little bit strange. We'll play with that a lot earlier, but most of our sets will be more concrete. So basically my rule thus far is a set is a collection of elements, objects, and you can determine if something in your universe is there or not. Often we write a set in what they call set Miller notation. Let me read this. These curly braces are often used for denoting a set. The set of all X in our universe, for which P of X so some examples. Let's see. You might consider the set of all even natural numbers. Here implicitly, my universe is the natural number, right? And I could also like this is set n and n such that n is zero. I could write this is set n and n such that n equal to n. So n and n. There's lots and lots of ways that I could write this set in the set builder notation. You all have seen this probably as well. You might have even seen it in calculus. So this is all real numbers that are between 1 and -1, inclusive. Right, so that's just that closed interval from -1 and 1. Right? You've probably seen this kind of thing in calculus, right? Um, Here is a very important policy set. I want to look in my universe, whatever my universe may be, a set of all X, it's not equal to itself. There is no such thing, right? This is a set. This is called the empty set. Set with no elements at all. So when you see this notation right here, this means the empty set. It's a set with no elements at all. Um, Definition. We say, I want to define the notion of subset. What do you think? What do you think a subset should be? What does it sound like it should be? Right, it's sort of like a little baby set inside the parent set. A subset. A V is a set within B, contained B. So let me be precise about that. So that's kind of my intuitive definition. A is contained to B if and only if for all X, X is in A implies X in B. So to be a subset, it's just some sub collection of stuff in here. If you're in A, you have to be in B. So B is sort of, in a certain sense, a possibly bigger set containing A, right? On the other hand, let me make the following observation when it comes to subsets. If A is a set, then I can automatically think of two subsets of A, for sure. Anybody name me one set that I don't care what the set is, automatically a subset? Yes. Ooh, good. The empty set is always a subset. For all X, X and A, there is no X and A, so this is false, so that's true. So the empty set is always a subset. There's another. Yeah. A itself. I can also think of a set that only has one subset. The empty set, right? It would have to be the case that the empty set and A are the same, because I listed two things here. And the only way that they're the same is if A is the empty set. Let me give you a simple set here. Let's subsets. See if we can list all the subsets. Okay, that's it, chance. I got the easy ones, right? The empty set and the whole thing. Are there others? Okay. 1 by itself and 2 by itself. Everybody agree? How about this? No. Well, let's go about this in an organized fashion. How many subsets of this have 3 elements? Just one of them, right? So one of them is all of the itself, right? How many subsets have only, say, I guess the next thing under 3 is 2. How many subsets have 2 elements? 3 of them. Think about it this way. You can kick out 1, you can kick out 2, or you can kick out 3. So kick out 1, kick out 2, kick out 3. What's smaller? How about 1? How many subsets have just 1? Good. Yeah. Just separately. And how many subsets have 0? Move the empty set. How many subsets were there now? Had 4 last time, something like that. Well, should I do an example where I look at let's see if we can list the subsets of an element, a set of 6 elements.
That, 64.
It'll turn out that we're 64 subsets. This is not a coincidence. It turns out that the number of subsets is equal to 2 to the, however big it is. By the way, this is, and I'm being very fast and loose here. It's kind of a teasing layer. That's even true for infinite sets, so to speak. The number of subsets is bigger, and we're actually going to see this. But okay, any questions? Let's look at the following proposition 214. That A, B, C sets. One. The empty set is a subset of A. 2, A is a subset of A. We've already discussed this a little bit. If A is in B and B is in C, well, suppose A is a subset of B and B is a subset of C. What conclusion do you think we can come to? If A is contained in the possible bidder B, and in turn B is contained in the possible bidder C, then A must be contained in C, right? Because it's the little one on the bottom, essentially. Okay. Let me kind of point to the details of this a little bit. Probably gonna be good for us. Recall, this is our definition of subset. A is contained in B if and only if for all X, X is in A implies X. If I tell this means for any given X, if it's in A, it has to be in B. So one, why is the empty set a subset of any set? Well, if, well, statement X is in empty set is always false. Right? Because there is no X in the empty set. That's how the empty set is defined. Right? So look at this statement. Remember, when you have a false premise, the simplification error is always true. So, empty set, A to negative. Any questions on that? For the second statement, if X is an A, X is an A, right? So A is a subset. Three, this property, by the way, anybody know what this property is called? If A is connected to B, B is connected to C, and A is connected to C. Have you ever heard of transitivity? Right, this is what this is. We'll see transitivity over and over again, right? Like, for example, you've seen it used before. If X is less than or equal to Y, and Y is less than or equal to Z, then X is less than or equal to Z. Transitivity shows up all over the place. And it doesn't show up in college football because otherwise nobody would go to the games, right? Because if this one loses to this and this one loses to this, then this one has to, and that's not going to happen. Yes. Is there a question? Yes.
One thing that's transitive.
I'm sorry.
Aren't things transitive?
Aren't?
Yeah, in like math, obviously football example.
Right, well, and of course, this kind of thing happens, if it happens in football, it happens all over math. You know, but there are lots of things, usually a lot of mathematical structures and properties that we look at are transitive because that makes things, you know, naturally occurring, things like inequalities, things like being contained in a set or whatever. But there are certainly things that are not transitive, right? Game theory. How many of you have ever decided things by playing rock, paper, scissors? Right? You ever done that? Right? That's not transitive because paper is beat by scissors, scissors is beat by rock, and rock is beat by paper. And that's why rock, paper, scissors works. Because otherwise everybody will pick the one that beats everything every time. Then you go. How about this last one? The transitivity. Then for all X in A, we have if X is in A, then we have X is in B. But now, since X is in B and B is contained in C, then X is in C. So if X is in A, then X is in C, and we have questions on that. Okay. This is a good place, I think, for us to stop today. Any questions? Yes.
Explain one again.
What did I do now? Oh, right. This is the formal statement for what it means for A to be contained in B, right? So here, let's modify this. What we're trying to say is let's revamp this. If you said it's contained A, if and only if for all X, X in empty set implies an X is in A, right? That's exactly this definition kind of reword what we're doing. This statement right here is always false because there is no X in A. And the implication arrow, we can do it this way. X implies Y is always true if X is false. And so what does this mean? This statement right here is true. And so empty set is true. Is that clear? Yeah. Okay. All right. Y'all have a good one and we'll see you on Wednesday.